Hi, and here we are with the other example for the week number 5 tutorial. So we start with this example, and this example we have a spatula which is have the weight of 80 kilogram, and the mass center at the point G. The mass center is located. That's mass center located at the point G, and the radius of gyration is about the point G of 1.2 meters. Now we need to determine what will be the coefficient of static friction at the point A if it's observed that the slipping occurs where the theta value is equal to 30 degrees, that's the theta, at its release from the rest when the theta was equal to 0. So it was upward released, and then the slipping will occur where the theta value will be equal to 30 degrees. So the free body diagram can show me what are the forces we can have on this bar. First, we have the weight at the center of the gravity, as usual. We can see that because it's vertical, so it's going to be different from the inclination line by 30 degrees as well. The distance from the point A to the center of gravity is 2.5 meters. We have a normal force, and we have a friction force, which is equal to the coefficient of friction multiplied by the normal force. The kinetic diagram here can show me that the mass multiplied by the acceleration is going to have two components that cause at least the moment around the point A if we're going to have the tangential acceleration to effects on the bar. The other thing we can have cause a moment around the point A is going to be the mass multiplied by the moment of the inertia, mass moment of the inertia for the bar multiplied by the alpha. So these are the components we're going to start to do the work on. Okay, so the solution that I provided to you is show us that we are going to use the free body diagram and the kinetic diagram after drawing to analyze the three main equations, which are the forces in the free body diagram are equal to the forces in the kinetic diagrams in the x and the y direction. The same thing is going to be for the moment. By using that, we will find that the value of the alpha is equal to 3.19, and we are going to write down the alpha as a function of the theta and make the integration for both sides in order to find the answer for the value for the mu. And this will be done by finding the normal force and the friction force and then calculating for the value of the mu. So again, we are going to sketch the free body diagram and the kinetic diagram. I know that we have them in the answer sheet, in the question sheet, but I'm going to make them once again more simplified. So that's the shape. We're going to have the weight affecting in the middle at the point G downward. The friction force trying to resist the movement of the bar to go to the left, so it's going to be pushing to the right, and normal force is pushing upward. The relation between the NA and the F is that the F is equal to the NA multiplied by the coefficient of friction. Now the kinetic diagram, once again, we're going to say that the acceleration at that point is going to be divided into two components, which is going to be the normal and the tangential. That we consider that we have a bar or link from the point A to the point G, and these two components of the acceleration will be used to find the forces, and then we can calculate the moment around the point A. The other parameters we have is the mass moment of the inertia around the point G multiplied by the value of the alpha, which is going to cause a moment around the point A to the clockwise direction in this scenario. We list the parameters given to us. The mass is given, the kg is given, or radius of gyration. The omega is 0 at this point, and that's actually when the value of the theta is equal to 0. So the value for the unknowns are going to be the friction force, the normal force, the omega, and the alpha, where the value is equal to 30 degrees for the theta. The equation is that the forces to the x direction are equal to the mass multiplied by the acceleration to that direction. The forces to the y direction is equal to the mass multiplied by the acceleration to the y axis, and finally the moment around the point G is going to be equal to the Ig multiplied by the alpha, or the sigma of the moment around the point A is equal to the sigma of the moments around the point A in the kinetic diagram. So we start solving. So starting again with the free body diagram and the kinetic diagram, and we start to do the calculation first for the magnitude of the accelerations we have there. So let's sketch my solution for that, and we can start from the point A to the point G. We can sketch a line, and this will be considered as a link like the one we done earlier, link AB. Okay, and the link AB is going to have the omega. Let's say the omega is going to be in that direction, and it's going to have the alpha. So that's the omega, that's the alpha. So you remember that we're going to be able to find what will be the magnitude of the velocity of the point B, BB. It's not required here, but what's required is the acceleration. So remember that the acceleration is going to have two components. One of them is going to be tangential, which is the A tangential here, and that's perpendicular to the link. We call it tangential because point B is going to rotate the link around the point A, is going to make a line, making a circle, sorry. Okay, so this line, this point is going to be tangential to it. The other one is going to be normal, the A normal. So you remember the equation for the A normal is going to be related to the omega, the A tangential is going to be related to the alpha. So the equations we have are the normal acceleration is going to be the omega squared multiplied by the r of the G slash A, or the point between point A and G. The same thing for tangential is going to be the alpha multiplied by the r G slash A. So now we can substitute the value. Remember that we don't know what the value of the omega, we don't know what the value of the alpha. So we can simply just substitute the value for the RGA, which is 2.5 meters, and the equation will be written as the omega square multiplied by 2.5, and this will make it 2.5 omega squared meter per second square. And same thing for the tangential, 2.5 alpha. Okay, and we can make the AG can be written as a vector of two components, which is going to be along the x-axis and the y-axis. So I can bring the tangential to the x-axis and the y-axis, where you can see that this component is going to have two components. One of them is going to be horizontal, going to the right, and vertical, going downward. The same thing for this acceleration, as can go to the left horizontally and downward vertically. So simply the sine and the cosine thing, and we put the signs to show you that these two components for the tangential, for normal, is going to go downwards and to the left, and for the tangential is going to go to the right. Let's make it positive here, and downward, which we're going to make it negative value. So now we're calculating the Ig, or the mass moment of the inertia. You remember that we said last time that the radius of gyration is going to be equal to the Ig divided by the mass under square root. So if I have the radius of gyration, I can simply take to the power 2, multiply it by the mass, and this will give me the mass moment of the inertia with this equation. Okay, so we have been given the value for the kg, radius of gyration, and we have the mass 80. So it's going to be 1.2 square multiplied by 80, and this will be equal to 115.2 kilograms meter square. So we're almost there. And I have the IG now. I would like to calculate these two forces, the mass multiplied by the acceleration and tangential, and the mass multiplied by the acceleration normal. But first I get to calculate the accelerations to the x and acceleration to the y. So these two components will represent the acceleration on the x-axis, and these two components will represent the accelerations to the y components. So simply adding these two will give me the x, adding these two will give me the y. So I can write down the two equations as following. That's clear. The positive and negative, depending on the clockwise or counterclockwise, or negative and positive, and so on. Okay, now we go to the next step of the solution on the next page. So we start with the basic equations for the signal of the forces to the x-axis equal to the mass multiplied by the acceleration to the x direction in the kinetic diagram. The signal of the forces to the y direction in the free body diagram will be equal to the mass multiplied by the acceleration to the y direction on the kinetic diagram. And finally, the signal of the moments around the point G in the free body diagram will be equal to the Ig multiplied by the alpha in the free body in the kinetic diagram. We will check that and see if we're going to reach a solution for the alpha and solution for the coefficient of friction. So we start first with the first one. The F is going to be equal to the AT multiplied by the acceleration to the x direction that we calculated from previous step. That's equation 1. Equation 2, again do the same thing. The forces to the y, which are the NA upward, the weight downward, that's in the free body diagram, is going to be equal to the AT multiplied by the acceleration to the y direction in the kinetic diagram. So substitute the value we have there, and we're going to get the equation 2. Now we have two equations. In the first one, we have three unknowns, which are the F. Okay, where's the pen? We have the F. That's the first one. We have the omega, and we have the alpha. Three unknowns in this equation. And we have 1, 2, and the 3 in the second one. I know that we have a relation between both the F and the NA, which is going to be the mu. But still, I don't know even what the mu is, and this will make it 4 unknowns in 2 equations. Okay, now let's try to find another equation and find a solution. So we're going to go to the moment equation. So we're going to write down the parameters. Let's go to the free body diagram. If I get to multiply, we're doing the moments around the point G. So the W is going to have no effects, and these two forces have no effects on the moment. But what we're going to have making the moments is going to be the Ig alpha. That's for the kinetic diagram. For the free body diagram, we are going to multiply the F, okay, by that distance. And this will make it to the counterclockwise. And we're going to multiply the NA by the horizontal distance. How we can find that? It's 2.5 multiplied by the sine and the cosine of the 60, because this angle is 60 degrees here. And we can find these two dimensions. So anyway, I'm going to substitute that now. Okay, the distance from G A in the y direction is going to be equal to 2.5. That's the triangle. Okay, so this will be the x direction, and this will be the y direction. That's 60 degrees. And that's 2.5 meters. So now you can find that the y is going to be equal to 2.5 sine, and the x is going to be 2.5 cosine of the 60. So we just put that here, okay, and we are going to find the answer to be unknown. Now let's see how much we are going to have here. We have the alpha unknown, the NA unknown, and the F unknown. So we have three equations, and we have three unknowns, but this is not going to help to solve anything. Oh, we have four unknowns here, which is the F, the NA, and the alpha, and the omega. So four equations, four unknown, three equations, and this is not going to help me to do anything. So let's try the other option. The other option is going to do the moments around the point A and let's see how it's going to work with that. Okay, now let's check the other equation, which is going to be moment around the point A. Now let's repeat the same steps. Now the W is going to make a moment around the point A in the free body diagram by multiplying W by the horizontal distance between the G and the A. That will be clockwise direction, and this will make a negative. Now on this side, around the point A, this can be the MAGT multiplied by 2.5 distance. That's the only moment part I can have with the force, and I'm going to have the IG alpha as well. So the IG alpha, we know the IG, we don't know what the alpha is. The mass is known, the acceleration will be given to me in terms of the alpha, so I have two unknowns here. The weight is known, so I can find the value for the alpha. So substitute that here, the weight multiplied by 2.5 multiplied by the sine of 30. That's for the horizontal distance. And we're going to have here the alpha multiplied by the IG. The alpha is negative, so this will have negative value here. And finally, we're going to have the mass multiplied by the acceleration tangential multiplied by the 2.5. Once again, because this will be to the clockwise direction, and this will make it as negative. Okay, so everything is negative here. I can change the sign to be all positive. Anyway, I can find here that the alpha is equal to 1.595 radian per second square. Basically here, this is not going to give me a solution, direct solution. But you can see here that we have 1.595 radian per second square. We know the alpha is a function of theta. The alpha is a function of theta, as what we have in the case of the omega. So I can simply write down the equation to be that the alpha is equal to 3.19 sine of theta. Can rewrite down this equation. I will explain that to you further very soon. So now we're going to write down the equation that we use in the tutorial 1. Okay, that the alpha multiplied by the d theta is equal to the omega change of the omegas. And now we're going to substitute that in the equation. The initial theta is 0, the final theta is 30. The alpha d theta, we're going to do the integration between these two limits, is going to be equal to the omega initially was at rest, which is 0, and the instantaneous omega, which we don't know how much. So now we can do the integration for both. Okay, and we will get that the value of the omega can be found now. Okay, now it's very easy. We just did the integration. Okay, we can solve for the omega, and omega is going to be equal to 0.92 radian per second. Now that's it. I can simply substitute that in the equation 1 to find that the F is equal to 190.8 Newton. And the same thing, I'm going to substitute the alpha and the omega in the equation 2, and I will get that the Na is equal to 477.2 Newton. Now, if I'm going to divide the F by the Na, I will get the value for the mu, which is going to be equal to 0.4. Okay, so now let's try to think about, okay, now how we change the 1.595 radian per second square into 3.19 sine of theta. Okay, so that's what we're going to discuss in the class. Now we can have another method to do the solution, and I'm going to show you that in the next page. Okay, so let's do an alternative method for the dealing with the direction of the alpha. Assume as alpha to be positive. Now once again the accelerations are given. These are the acceleration equation we found earlier. We're going to do for the x direction that the F is equal to the mass multiplied by the acceleration x. The y direction, the weight plus the Na equal to the mass multiplied by the acceleration gy. That's we're going to the other direction. And then for the c, it's going to be the weight multiplied by the distance between the a and the I. That's in the free body diagram. Okay, is equal to the Ig alpha plus the mass multiplied by the IGA expression of the point G, tangential multiplied by the RGA. So now we substitute the values in. That's the same equation we got earlier. And this will be the second one, exactly the same, except that the sign has been quite changed. Now we go to this one, we just substitute the parameters in, and then we can solve for the alpha, and we find the alpha is equal to negative 1.595 radian per second square. Now, how do we got the 3.19? So if I'm going to divide that by the sine of 30, which is the angle that we have, okay, this will give me the 3.19, okay, which can be multiplied by the sine of theta, which is 30 at maximum, okay, and that's how we solved for the alpha. Okay, so thank you very much, and we're going to have more discussion about the other questions later.